in Arizona. We do high temperature chemistry. Sometimes we can do it just by stepping outside our door. What I'd like to do is really a more general presentation from the title that you initially had, in part because Jerson will have a talk on the work that we've done so far on fibers, and I would like to put this a little bit more in the general context. So the next slide hopefully does this, but before that I would like to remind people, not everybody, that I moved from UC Davis to Arizona State University about almost 2 years ago, actually 2019, both to start my research program in different directions, and we have a new lab with a lot of new equipment, and to head up a new Center for Materials of the Universe. So from a material science point of view, the excitement we see in the exploration of the outer planets in the solar system, and of course Mars and Venus as well, and from the myriad of exoplanets that are discovered, is really the biggest inverse problem in material science. The forward problem is here's a material, what is its properties? An inverse problem is here's some measured properties for something light years away. What might that something be and how might it have evolved? A second point is that one needs new materials for aerospace and space exploration, materials that are more radiation tolerant, materials that perhaps can be made in space, etc. So the Center for Materials of the Universe addresses both of these by involving faculty, and we have some faculty hires to address these questions. What does this have to do with polymer-derived ceramics, fibers, and so on? The first thing, of course, is that some of the materials that we're improving may actually be very useful for various high temperature and intermediate temperature applications in aerospace. The more, to me, intellectually interesting thing is that what we discovered from polymer-derived ceramics is that one can make similar materials, for example, by condensation from gas phase or by condensation from something that has been barded. So it begins to look as though perhaps some of these materials could be made in nature, particularly by impacts. And if that's the case, then stably or metastably, materials like polymer-derived ceramics, like silicates containing additional amounts of carbon in their structure, like all sorts of new materials, might exist in different environments. I remind you or tell you that materials, major impacts, such as that which may have formed the moon, would vaporize a good bit of the planet, and then that material would condense very quickly, and one would get all sorts of stable materials. Secondly, there may be exoplanets that are carbon-rich, and in those certainly carbon polymorphs, but also silicon carbide and various other materials might actually be major planetary constituents. So materials of the universe and the things that we're working on here may actually have something in common, and we're continuing to explore this. But that's not the major topic. I'd like to basically review some of the things which already have been reviewed to some extent, but I think putting them together is useful. So again, this just summarizes the materials of the universe idea and our center and the sort of interdisciplinary topics that we might cover. Let me save time and go on following slide. So the question then is, do silicon carbide, oxycarbide phases exist somewhere in the universe, on Earth, on carbon-rich planets, on the outer planets, etc. Next, please. Let me talk a little bit about calorimetry. That's what we measure enthalpies of reaction. Why do we do it? We do it basically because it tells us a lot about what phases are stable, what phases are possible, but equally importantly, tied in with spectroscopy, crystallography, computational work, tells us a lot about the molecular level forces that make materials stable, including things like polymer-derived ceramics. So what we do is measure enthalpies of formation of materials by high temperature oxide melt solution calorimetry. We measure heat capacities, in part cryogenic heat capacities in collaboration with Brian Woodfield at Brigham Young University. Transformation decomposition reactions. The major things that we have here at ASU are equipment for oxide melt solution calorimetry, standing calorimetry. I will also mention that we have a new, what is called flash calorimeter, something that is made by Mettler Toledo. It's a calorimeter based on chip technology. It takes very small samples, microgram size samples, but can heat them at huge rates, up to 1,000,000 degrees a minute, cool them similarly, and look at phase transformations. It does occur to me that some of this variation in heating and cooling rate may actually be very useful in thinking about the processing of ceramic polymers, and I'm just beginning to think about that, and maybe this afternoon we could discuss some possibilities. So, next. What high temperature oxide melt solution calorimetry does is it dissolves components, reactants, and products in a molten oxide solvent to make a dilute solution. Differences in the heat of solution of reactants and products give the heat of formation. We can deal with oxidative reactions for nitrides, sulfides, selenides, carbides, oxycarbides, polymer-derived ceramics. And these are needed in general for ceramic refractory materials that don't dissolve in aqueous solvents, which certainly the PVCs and fibers and so forth are a category of. Next then, this is the calorimeter that we now have. We have 2 of these at ASU. Our own calorimeters have been commercialized by Cetaran Technology, and we effectively have 2 of these then in the lab at ASU, and they are working very well. One was brought from Davis, one was purchased new. The calorimeter itself, next slide, is a heat flow calorimeter. It measures effectively the temperature difference between a bunch of sensors cylindrically surrounding the sample chamber. That temperature difference is created by the absorption or emission of heat during a chemical reaction. That temperature difference drives heat flow. The heat flow measured over time, integrated over time relative to an apparatus baseline, gives the enthalpy of reaction. The calorimeter is calibrated appropriately. The actual experiment then consists of dropping a small sample, typically a few milligrams, 1 milligram to 5 milligrams, into a molten oxide solvent. If we want the material to oxidize, we pass oxygen through the solvent. Typical solvents we use are a lead borate melt or a sodium molybdate melt. And I would say now our calorimeters, commercialized calorimeters exist in a number of other laboratories, and we're very proud then that basically these laboratories are becoming independent and able to do things without our help, without our names on the papers. This means that the technology is much more available. The next slide then looks at materials in the silicon, carbon, oxygen, nitrogen system plus metals. Materials is the general, shall we say, generalization, which forms PVCs but other materials as well. Carbon itself, polymer-derived ceramics, metal organic frameworks, and then of course fibers, which are the main thing of interest in PIRE, but which form only part of our big research programs. Next. So diamond graphite transition in carbon, of course, is well known. There are many, many forms of graphite that are somewhat different. They are more or less understood, but sometimes it's less. There may be work that can be done. More interestingly, there are nanodiamond, diamond that's partly transformed to carbon, beetles of carbon things, etc. Gabi and I have been planning to work on a number of these things planning for a couple of years, but the COVID shutdowns have slowed us down. We will get back to it. Calorimetry basically is intrinsic in understanding the stability. Initially, we wanted to get the surface energy of different forms of carbon, and we found that the energetics we measured seemed to indicate that the nanoscopic forms of carbon were more stable than the macroscopic forms, which is nonsense. And we realized that surface oxidation is intrinsic to these materials. You cannot make them for all practical purposes without having some organic oxidized functional groups. On the surface, you can control those functional groups to some extent, and we strongly suspect that, in fact, these nanoforms of carbon are absolutely stabilized by these functional groups and may not exist without them. So this is something to consider as well for our polymer-derived ceramics, for the interaction of the fibers, the silicon carbide, and so on, that one isn't necessarily simply in the chemical system one would like to be in. One is in a more complex system. And, of course, the surface and interface energies and the interaction then for the fibers of, let's say, the PVC fibers with silicon carbide, with whatever else is present, is really critical to their stability and their function. So next, polymer-derived ceramics. I think we know a lot about them. What I want to stress is that what we found now more than a decade ago is that, in fact, they seem to have stability of their own relative to crystalline silicon carbide, crystalline silicon graphite. And this is very interesting because it suggests that they are actually possible phases formed by methods other than totally metastable means of pyrolyzing organics. And this indeed we did find, as I think the next slide suggests, that basically we have the enthalpies of formation are negative. This may explain why the samples are relatively stable. They don't really decompose to a carbothermic reduction of silica above 1500 degrees. So the question is, does a complex synthesis route, is it really necessary? Does one have to deal with nasty toxic chemicals? Or, for example, does nature do it on its own using different ingredients? And indeed, what we found, which the next slide shows, is that we can do vapor deposition and laser ablation of a silica target, which we did in an acetylene atmosphere. It produces nanophase SiOCH materials, which are like the PDCs, except they contain larger amounts of hydrogen, and we've looked at their thermodynamic stability. So there may be many ways of making related materials, and indeed materials related to the polymer-derived ceramic precursors are interesting from the point of view of low dielectric constant filler materials, and we actually had some funding from Intel to study the thermodynamics of those materials several years ago. Next. So again, the suggestion then is that these things may actually form in the natural environment, and that materials that contain silicates with carbon in their structures may be more prevalent than we realize, and they should be looked for in a number of environments, including impact environments, exoplanetary environments, etc. And I think we just scratched the surface of the existence of such materials inspired by polymer-derived ceramics. And here I coin a new term. We talk about geomimetic synthetic materials. Material science imitates nature in the sort of materials it can make and the mechanisms by which it can make them. But if one looks at more extreme conditions that we use for chemical synthesis and for new materials and technology, and then we say, do similar processes occur in nature, perhaps under extreme conditions, unusual conditions on Earth, usual conditions on other planets, we can think of these processes from our selfish anthropomorphic point of view as technomimetic. We discover processes in technology, we think we've made something new, maybe nature's done it for billions of years slightly differently. This fascinates me, and we are starting some research along those lines on a small scale. So next then, if we take a look at metal organic frameworks, this is a different set of materials. It is a set of materials analogous to zeolites, sometimes called zeolites on steroids, because their pores are so much bigger. And I think here, yeah, we have a couple of things to add to this slide. We'll go to the next. So the pore space then in these materials is huge. The PET surface area, for example, of this particular material is immense. And click again. In an ideal degassed material, something on the order of almost 100% of the space is free space, and these big yellow balls, which Omar Yagi has used to indicate the free space in these materials, gives you a notion of the structure. So there's the framework, and then there basically is the free space in which one can play, or nature can play, all sorts of games. The next slide shows the energetics of zeolites, shown in the cool colors, and of metal organic frameworks, shown in the warm colors, as a function of the molar volume. So you start off with a low molar volume for dense phases, and you increase the molar volume by factors of 2, 3, 4, 5. The energy goes up, but not hugely, and that's interesting. And the energy appears to sort of level off at high porosity or high volume. That is, you're finally creating free space that in itself does not affect the stability of the materials. So this is tremendously good news for material synthesis people. One is really not energy limited in these materials. One is limited by one's imagination in synthetic techniques. And there are all sorts of fascinating synthetic techniques for metal organic frameworks, including mechanochemistry, which again, I don't have time to go into. Next. So basically then we see the same sort of thing in a series of metal organic frameworks where we have true polymorphs. That is, we have the same composition but different structures. And we show that with increasing synthesis temperature, extent of grinding, and so on, we make different polymorphs. They are denser than the initial material made by conventional solvent thermal synthesis, and therefore one is marching down an energy landscape toward the more stable dense form by increasing the synthesis duration or the mechanism or so on. And this then is an energy landscape that follows essentially a decrease in instability or increasing stability, and whether the same sort of transitions occur even in polymer-derived ceramics, as one would in yield of more, we do not know. But this is essentially the way these materials work, and we've seen them for a number of materials. There are also a number of naturally occurring metal organic frameworks, which we have investigated to some extent. So these are minerals which effectively have these sorts of open structures and have organic to them. Next, and I'm really almost finished here, we basically look at the effect of peripheral substituents on the materials. That is, we have large organic linker groups. And those linker groups are not simply some sort of scaffold holding the metal nodes together. They are absolutely active in the process, in thermodynamics, in the mechanical properties, in the transport properties. They rock and roll and wiggle with temperature, and we have to think about the same sort of thing, I believe, with polymer ceramics, that they're not inert. The framework part is a major actor in the structure and dynamics of the material. Next. So the conclusions: the stability in the box decreases with increasing volume, but the effect may level off. The synthesis goes downhill through a complex landscape of polymorphs, and the organic linker plays a major role in the structure of thermodynamics. How much have I run over time?
Oh, you're right on time. Good.
I'm right on time. Okay,
Good
then I can finish off the fibers. So the work is done basically by my student who is here, Jerson, who's a chemical engineering PhD student. It's in collaboration with Graphite. Jerson came to us from Washington State University, where he was an undergraduate and where one of my graduate students worked a lot on metal organic frameworks and other things. Dean Wu is a faculty member in chemical engineering. We've looked at the calorimetry, and we seem to see that the polymers with more impurities, oxygen and nitrogen, have stronger stabilization interactions, and actually then we will see presentation of work in progress from Gerson's talk. The next slide then basically is a universal conclusion that in all these classes of materials, the interactions between the organic and inorganic components are serious. They play a major role. They may play a major role in the stability. They major role in the transport properties. Major role in the vibrational electronic density of states. Nanoscale and surface effects are indeed important, crucial to the stabilization of these materials. And there are various ways of stabilizing these nanomaterials, both through enthalpy and entropy effects, so they're not necessarily always metastable. So, to conclude, I hope this hasn't put you to sleep, but this is how my dogs react to thermodynamics. Thank you.